Greetings. Welcome to my new calculus channel. My name is John Gabriel. Today, I'm going to continue with the fifth lecture in the series that I've started on the single variable new calculus. So let's begin. If you recall, excuse me, I gave 4 lectures on the first 4 chapters, and the last one was on the topic of axioms or postulates in mathematics. So, excuse me. In this chapter, I'm going to deal with how we got numbers. The next 2 chapters actually lay the foundations of, the next 3 chapters lay the foundations of all of mathematics, because numbers are the most important object in mathematics, and without the arithmetic mean, there'd be no calculus. So, how we got numbers is quite intriguing because no academic before me actually understood it. And there are several reasons. Do you recall that when we discussed what it means for a concept to be well-defined, and the fact that in Greek mathematics, we had a translation from the original text in which it wasn't clear to the translators what certain words meant, and how they went right off track by assuming that the 5 requirements are actually axioms or postulates, which they're not. And I showed you in chapter 4 how to derive all those 5 requirements from absolute nothing, right? And given those requirements are in place now, it's very easy to define numbers. So let's go to chapter 5, how we got numbers, and just use it as a guide. All right, so chapter 5. We'll look at a thorough derivation of number from nothing. In other words, a perfect derivation, and see how to understand the concept of number, okay? And as we saw, academics of the last century or so failed miserably to reconstruct the foundations. And what they ended up was with a load of garbage called set theory, Zermelo-Fraenkel axioms, and a foundation that is supposedly based on set theory, where the very object of set itself is not defined to begin with. And now we're going to look at how the Greeks did it, and also see that Euclid tried to write down the perfect derivation. I'm pretty certain, in fact, I'm 100% certain that the ancient Greeks knew how to derive number. Euclid had some not so well-formed definitions. For example, he had some circular definitions, and circular definitions are not well-formed. They tend to be confusing. And of course, a circular definition doesn't really tell you what is the object if it's being defined in terms of itself. So it's not a well-formed definition or a good definition, as opposed to a bad definition, which is ill-formed, okay? So now, it's no accident that in book 5, Euclid defined a magnitude, okay? And really, what he should have written down is this. He should have written down a magnitude is the idea of size, dimension, or extent, because that's obviously what he meant. And much later on, after chapter 5, we get to after book 5, we get to book 7, where it discusses the definition of a number. But before we look at all of this, let's just see if we can very quickly ourselves define numbers. And it should be very easy to do now. Now remember, we know what straight lines are. There are certain distances, right? So we've defined that already. That's taken care of. So now, the idea of number is realized through measure. And at first, it's a quantitative type of measure. So for example, if you have two lines like this, and you can obviously tell that they're not of the same length, right? Doesn't really matter. I'm not going to get that exactly straight. But anyway, they're not exactly of the same length, yes? And if we can tell that they're not the same line, we know which one is shorter or which one is longer, because we can tell qualitatively that this red line is longer than the black line, okay? But that's just a very weak measure. All it does is it tells us that this distance here is longer, but not how much longer it is than the distance denoted by the black line. Now remember, a line is just a visualization of the perfect concept of distance. In other words, we're talking about the length between the endpoints, okay? So between 2 points on here, one on this side and one on this side. The line is the distance between 2 points. So qualitative measure doesn't really tell us very much, and we may not be able to proceed very far if we can't tell that the lines are different. So for example, if the black line was exactly the same as the red line, then all you can tell is that you think they are the same, but you're not even certain that they are the same. Okay, so qualitative measure is very poor. But we need to start off with qualitative measure, because qualitative measure allows us to compare one magnitude, like so, to itself, right? And when we compare this magnitude to this magnitude, the length of this line to this line, we realize the idea of a unit. And we can basically write down our unit like that. Moreover, if we had another line of this distance on this side here, like so, added to adjacent to this line, then we get I didn't mean to do that. We get a new object. We get a new object, which is the definition of the number 2, right? Because 2 is now the ratio of this line to this line, right? Whereas before 1 was really the comparison of this line to this line, and 2 is a comparison of this line to this line, right? Similarly, a half would be the comparison of that line to that line. Now, the line that comes first is called the antecedent or the numerator, and the line that comes after is called the denominator or the consequent. Now, remember here, we don't even have numbers yet. So we could symbolize 1 like this, okay? And then we could symbolize 2 like this. Put another one there, like so. All right, never mind. And another one like so, right? So this here is 1, and this here is 2, right? Okay, so so now we can basically write down any magnitude, provided it consists of multiples of a unit or parts of a unit. Because if it's a part of a unit, then we simply choose the unit itself to be one of the equal parts of the unit, okay? And we just, so for example, 2/3, right? So if we had 2/3, 2/3, it would be 2 of those, right? And 3 of those, right? In other words, we just choose the unit to be one of the equal parts of this, which is now the unit, okay? So this is the unit, and this here becomes one of the equal parts, right? Does that make sense? Okay, so now what is the difference if we had to choose this red line to be the unit? Then our unit 1, or the concept we think of as 1, would be that, right? Now, what is different between this one and this one here? Can you think of what the difference is? Well, they're obviously not the same length, are they? So if we simply denote the number 1 by writing 1 like that, it doesn't have any units, okay? That is the abstract number 1. So it could be either this length or this length. It doesn't matter, because we're saying it is the abstract unit. So it's dimensionless. It doesn't have an extent in terms of magnitude. Okay. In other words, it could be any particular magnitude compared to itself. So that's why we have equivalent fractions, for example, right? Because if we had this and this, okay, so these both symbolize or represent a half, right? But now they're only equal if they're dimensionless. In other words, if we don't care about the actual unit or the magnitude unit, all right, which is this red one here or this black one here. We just care about the abstract number. So the abstract number in this case is 1/2, right? But obviously, this 1/2 here, this 1/2 here is not equal to this 1/2 here, okay? So while they're equal to each other in terms of dimensionless units, they're not equal to each other if units are of importance. So for example, if we're measuring in terms of this unit here, then this half is not the same as this half. Do you understand that? Okay, so there is clearly a difference between the abstract number and the number that is being denoted in terms of a chosen unit or a magnitude. This is a chosen unit and this is a chosen unit or a magnitude, okay? Because a unit is just simply the comparison of two magnitudes, right? Like so. So this is a unit and this is a unit. And you can have any length line and still you will have the idea of a unit. And so you see, using this scheme here, we derive from nothing all the rational numbers, right? And we just give them names. So we start off, we give this a name, then we add, I didn't mean to do that. Then we add, let me just grab one of these down here, that's why I have them. And we add that, and we add that, and we have the idea of 3, right? There's not actually spaces in between them. So this is the idea of 3, and if we want 1/3, that's pretty easy. We just do that, right? And if we want 2/3, we just put another one of these next to it. And 3/3, then we put another 2 of these next to this one, right? So we take this and add another 2 on this side, here and here, and the ratio is 3:3, which is 3/3 and is the same as 1, right? In terms of dimensionless quantities, right? In other words, we're only looking at the abstract concept of number. So now I think I've given you sufficient details of what it means to be a number and how to derive it from nothing. And this is how the Greeks did it. And if you go back and study the elements, book 5 and book 7, you'll see that the Greeks used line segments. And they were able to form ratios of first of magnitudes, as I showed you in here, first ratios of magnitudes and then ratios of numbers, right? So once you have the ratio of magnitudes, then you can form ratios of numbers. And my book explains all that in very fine detail. So I would advise you to read this entire chapter. Now, there are certain magnitudes such as pi and square root 2 and e and many others, for which the unit is not really helpful because there is no unit that measures those magnitudes. And since those magnitudes have no measure, there is no number that describes them. So pi is not a number. It's the name of the magnitude. It describes the magnitude, but the measure of it is not known. We can say, oh, well, it's 3.14, and we can go to as many digits as we please, but it doesn't matter how far we measure it. And that's what you're, in fact, doing when you're adding extra digits. You're measuring the magnitude. Okay, in either case of pi square root 2 or any other transcendental or so-called incommensurable magnitude, which, by the way, is not an irrational number, okay? A magnitude is not the number, but a number describes the measure of a magnitude. So to really understand numbers, you have to read this chapter and go through it and see exactly what all these things mean. And this is how children should be taught about numbers. They should be shown line segments or given different areas or masses or volumes and allowed to derive numbers that way. However, the simplest way to derive the concept of number is through line segments. And of course, the very first step, if you're teaching your little toddler, is to teach them how to compare things, okay? Because only through comparison do we measure. If you cannot compare things, you have no measure, because measure is comparison, okay? They're the same thing. So for example, you could draw a line like this and then a line like this and ask your little toddler which is longer or shorter. And then you could take these two away and ask him which is longer or shorter and see if he can figure out whether they're actually the same or not. So this teaches a young child how to understand the concept of number rather than the bullshit of set theory, okay, where you have something completely undefined like a set and you've got, which assumes the pre-existence of numbers, and you place objects in it and then you start associating the ordinal value of a set with a number. That's totally wrong. And that's how mainstream mathematics was infected by the vile ideas of George Cantor, Zermelo, Fraenkel, Russell, Hilbert, and all the other morons that came before me. Right, so the foundations, as you can see, are pretty straightforward. The Greeks laid the foundations. There's nothing to change. And an interesting concept is the concept of a number line. And this part of my chapter, in which I describe how we got number, tells you what it means to reify a number line and what numbers can be reified and what it takes to actually reify a point, because a point is really just an invisible marker. So you'd need to, first of all, be able to construct the line segments, to assign the markers as in calibration, and to provide a measure for each marker. And if you study this carefully, you immediately see there's no such thing as a real number, and you can never reify it, okay? And again, here I show you this same concept, which I described in my paintbrush here. And also the magnitudes are refused to be measured, such as square root 2 and all the other things. And then I go into this detail about what it means, for example, to be an incommensurable magnitude. In other words, a magnitude that is not commensurate with any other magnitude. And all this stuff is the most important knowledge that you need. I also debunk two mainstream constructions of numbers, the Dedekind cuts and Cauchy sequences. And in this chapter, I'll show you that both are not valid constructions of number. In fact, they're garbage. And this is what you learn in a course of real analysis. And it's a whole load of junk, which you don't need. It doesn't provide a valid construction of the mythical idea of real number. And the Greeks called those magnitudes that couldn't be measured incommensurable because they could not measure them, and neither could the morons that came after them. Okay? In fact, not even God can measure those magnitudes, or the gods. Right? So, this is quite a long chapter, but very important. And once we've finished with this chapter, we'll look at the next chapter in the book, which is how we got algebra, not a very long chapter, in a separate lecture. And then after that, the next most important concept in mathematics, which is the arithmetic mean. All right. So I hope you've enjoyed this little presentation. This is the New Calculus channel. Till next time, my name is John Gabriel. Goodbye.